Hello, my name is Igor and I'm going to present our work from real to synthetic and back, synthesizing training data for multiple person scene understanding. This is a joint work with Nadav Bonker and Gerard Medioni. We all know that accuracy of deep models is highly dependent on the amount of annotated data used for training. However, relying on manual annotations is problematic. For example, semantic segmentation label maps created by humans are expensive and inconsistent. Some annotation tasks cannot be performed by human annotators at all. For example, the per pixel dense depth annotation task. One useful alternative is synthetic data, where the annotations are automatically generated along with the synthesized content. In this work, we chose the social interactions in the CMU Panoptic Studio as our target use case. We started from modeling the Panoptic Studio in Blender based on the publicly available physical dimensions and the camera placement specifications. We modeled the humans using the SMPL parameterized body model, fit to the 3D skeleton sequences from the CMU Panoptic dataset. Finally, we placed the posing avatars inside the virtual studio and rendered the scenes using viewpoint corresponding to the actual cameras. As a result, we obtained highly realistic, synthesized images of the original scene. This way, we are able to synthesize multiple activities or the same activity with various combinations of actor appearances. These sequences are accompanied with highly accurate annotations, synthesized automatically as we can see from this video. The annotations are skeleton joints, dense depths and UV maps, and body part appearance and instance segmentation maps. However, as we can see, the avatars do look synthetic compared to real-life actors. This contributes to the synthetic to real domain gap, and we would like to reduce this gap as much as possible. We will now describe a scheme that we found useful in reducing this gap. We first train a scene parsing model using our synthetic data. The model segments the scene and the avatars into predefined semantic classes. For example, the floor, the walls, and the scene and the person's appearance. Next, we auto-annotate real data using the trained scene parsing model and train a conditional GAN on the opposite task of generating photorealistic scenes from a given semantic segmentation label map. Finally, we are generating photorealistic images of novel scenes by feeding the label maps synthesized in our 3D simulation into the conditional GAN. Here we present several examples of frames generated using such scene description label maps. The following 4 examples show exactly the same scene where we have preserved the poses of the actors. Note the variability in different actors' builds and appearances. Comparing to the state-of-the-art approaches such as CycleGAN and Cycera, the proposed CGAN achieves a better FAD score. Qualitatively, we also observe higher photorealism of our approach comparing to the original synthetic frames and the results generated by other methods. Close examination of the images shows that our method improves the photorealism of the generated faces, produces more consistent illuminations, and realistic folds in closing. To demonstrate the value of our approach to train deep models, we use the generated data to train a multitask network on the challenging task of UV mapping and dense depth estimation. We train the model using synthetic data only and apply it on real data. We measured the accuracy of the trained models for the tasks of 2D and 3D joint estimation using the CMU Panoptic dataset. We conclude that the increased photorealism of the data results in improved accuracy. Thank you. For more details, please refer to our paper.